Our speaker this evening was formerly a techie at Amazon, Greenplum, and Zillion. And currently he's the Cloudera Director of Product Manager. Please welcome Michael Crutcher.
So basically what I'm going to cover today is a brief intro to the technology. It's not super deep, but there's a relatively technical bit to it. And kind of the second half of the presentation is going to be from Cory, Isaacson, who's also joining us here. He's CTO at RMS, and he's one of the early adopters of Kudu. He's going to talk to you a little bit about like kind of the decision framework that they use to evaluate which technology they might use and kind of their experience thus far. So before diving in, if you didn't know already, you might have learned as part of the t-shirt giving away, Kudu is a new storage option for Hadoop technologies. It's meant to sit somewhere between the existing storage technologies, and we consider those HBase for NoSQL, kind of fast access, and HDFS for analytic access and big scans. Kudu is meant to be somewhere between those. It has a mix of the characteristics they both have. And the primary goal is not to be absolutely optimal with any particular kind of performance, but to be a healthy mix of the two. So a brief rundown of why we decided to build something new versus incrementally adjust some of the existing options that were there. Kudu is actually a relatively long-running project. It started about 4.5 years ago, and the genesis of it was basically we asked one of our most senior developers, a guy named Todd Limpkin, who's responsible for HDFS, HA design, responsible for a lot of features in HBase. But we asked him and product management to kind of step back from their day-to-day job and to look on a much longer time horizon and ask whether we had the right storage technologies to really take us through the next decade or so. And there are a lot of questions that went into that process. I'll talk about two of the more important ones. The first one is, are there any gaps in the current storage technologies in the Hadoop ecosystem? And again, we consider these HDFS and HBase. And I think that if you look at any particular type of workload, that there actually is a pretty decent answer. So HDFS basically runs at the speed of disk. It has very little overhead, very little metadata that it keeps. HBase is very good at doing individual lookups. And for the rest of the presentation, anytime I say HBase, I think it's fair to substitute in other NoSQL technologies, Cassandras, Mongo's, etc. They tend to share relatively similar trade-offs in terms of what they could have from a perspective. So for either end of the spectrum, for individual low lookup or big analytical scans, it's a good option. But we think there's still a gap, and that gap exists where you need these kind of properties simultaneously in a single storage engine. Up to now, there's not a good option for a storage technology that's good at analytics, that's good at updates, that's good at individual point lookups, and we think a lot of real-world workloads tend to have that mix of characteristics. The second question was, are we set up to take advantage of the changes in the hardware landscape that we anticipate over the next decade or so? And this is a bit convoluted, so stick with me for a second. But the basic premise is that the existing storage technologies in the Hadoop ecosystem were designed about a decade ago, where it was exclusively true that storage hardware was slow. It was all spinning disk. 10 years ago, Flash existed, but was deployed basically nowhere. And so if you're designing a storage system, that means that you design around the limitations of that hardware. And it meant that you designed around the storage layer being exclusively the bottleneck to overall system performance. But that's no longer the case. The storage layer is definitely getting faster. And we found almost exclusively that the next bottleneck you hit at the storage layer that's faster is at the CPU. And if you're going to design a next generation storage engine and you want it to be as fast as possible, you're going to design around the limitations of CPU and be as efficient as you possibly can. And that wasn't the paradigm that the existing storage solution built under. And so for those two reasons and a bunch of other stuff, we decided to build something new from scratch. We didn't think it was possible to achieve these design goals by incrementally making changes. These are pretty low-level architectural things that we need to have in mind when we're building the software. And obviously that new thing we built was Kudu. The overall design goals are to be near best of both worlds from a performance perspective. Again, not absolutely optimal with either, but pretty close. So to give high throughput for big scans, close to what you get out of HDFS and Parquet, to give you low latency for short access. So to give you around 1 millisecond access to individual rows if it's coming off SSDs. Basically, it's the same kind of performance you get out of Cassandra's, HBases, etc. To give you database-like semantics that are familiar to a wide audience that maybe extends beyond the open source ecosystem. Skills have been built up for a long period of time. And part of this, and I think a little bit of a consequence of achieving the performance, is that this is a typed system. And it is typed in a way where tables are the basic underlying structure. Tables have columns. It's a relational data model. And it's almost a new type of storage, basically a table store instead of a file store or an object store or a block store. A table is the fundamental abstraction. As you would expect from any next generation storage engine, Kudu is scalable and fast. Up to this point, we've tested 275 nodes, which is about a 3 petabyte cluster. We think it would scale into thousands or potentially even tens of thousands of nodes. There's an awful lot of headroom that we simply haven't tested because we don't have a lot of 1,000 node clusters sitting around. If you have 1,000 node clusters you'd like to lend me, we would definitely take advantage of it. But the overall point is that we think that it's good to scale into the tens of petabytes, potentially even like 100 petabytes. The number of data problems that it can address because of scale, I think is like very, very small, or very, very few 100 petabyte data problems that exist right now. If I watch this video in 20 years, that's going to sound really silly, but that is the case right now. It's fast. It can support millions of read and write operations per second. It supports multiple gigabytes of read throughput per node. In other words, it's very CPU efficient in pulling the data off disk and pushing it through the CPU. And even when the data gets really big, tables that are hundreds of billions of rows or trillions of rows, you still get individual row lookups that are very, very fast, mostly as a consequence of Kudu having a real primary key, but you can get down to individual rows very quickly. It supports consistent operations. As was mentioned in trivia, it is a CP system, a consistent partition-tolerant system, through a Paxos-like core model, which is wrapped, by the way, so you were right, you should have got a t-shirt. And it is open source under the Apache license. We're pretty proud that recently, in the last couple weeks or so, we did achieve top-level project in Apache, which is basically an endorsement that there's a healthy ecosystem and that it's not solely backed by one individual company. It is definitely true that Cloudera has done the most development work on it to this point, but we do have other contributors and are actively looking for anybody else that wants to contribute. It's definitely not a Cloudera-specific project. Top-level status indicates that that's the case. It's also important to understand what Kudu's not. It is a little bit of an abstract concept. This is a storage layer technology. But I'll talk about Kudu and basically as a consequence of tables being the underlying structure in the context of SQL quite a bit. But Kudu in and of itself is not a SQL engine. It doesn't have a planner or a parser or the execution engine that you see typically in SQL systems. It's just the storage layer. As an abstraction, it looks relatively similar to what you see underneath the legacy commercial database systems like Vertica, Greenplum, Exadata, etc. The underlying storage system that sits under MPP databases is relatively similar to what Kudu is. It's basically a bring your own SQL because you can use other SQL engines. I'll talk about integrations that we've done in a little bit. But if you have existing applications, it's possible that they can be migrated over to Kudu with basically no modification because you're interacting at a higher level than the storage layer. You're interacting with SQL. And so you can just kind of swap the storage layer and get a more attractive set of characteristics without application modification. It's not a file system. As I said, it is a table store. And it's also not an application that runs on HDFS. It's basically the same level as HDFS. It's not like HBase where it's HDFS plus some additional metadata structures to make it updatable. It is a from-scratch storage system at the same level. That does mean that you will have to make an upfront decision about how you want to allocate hardware resources. Kudu can run on the same physical hardware as HDFS. I would say right now there's no explicit workload management to dictate whether individual user queries are prioritized on one system or the other. There are ways to do this a little bit with containerization and some other techniques. I would expect us to have more explicit workload management in the future, but right now it's pretty weird. And also, probably most importantly, it's not a replacement for HDFS or HBase. I think it's an engineering maxim that if you try to optimize for everything, you can optimize for anything. Kudu is meant to be that middle ground that's good at basically everything, but not quite optimal at particular workloads. So if you have something that's purely scan-oriented, that's still an HDFS use case. If you have something that is an extremely sparse data set, that's still an HBase use case. We might have changed the Venn diagram of what workload is appropriate for what storage engine a little bit, but there are definitely still places for these. We haven't reduced our investment in either of these technologies, but they have a healthy life in front of them. So I'll talk about use cases really briefly. This is meant to be a more technical presentation than I would give to like salespeople or CEOs or whatever. The important thing from a use case perspective is it's not really a particular vertical industry or a particular set of things that it's good at. It's really more about these workloads all happen to share a mix of performance characteristics that are not adequately addressed by a single storage engine right now. So no matter which of these you look at, they all tend to have some amount of updates, some amount of short scans, some amount of analytical performance. That's really one of the two key identifiers for whether Kudu would be an appropriate replacement for something that you implement right now. So mix of characteristics appears across a lot of different vertical industries. The second kind of key indicator would be if you've built a convoluted architecture to kind of spackle over some of the gaps that exist with the current technologies. And what I have here is a design pattern that I've seen like literally more than 100 times at Cloudera customers. And this is basically a way to do analytics where your analytical systems are not updatable while still allowing you to do some amount of updates. So what a lot of people do is they'll use HBase or Cassandra or some other NoSQL system. It's like the active partition that is a subset of the overall data that can be updated in place. They'll then periodically take that data, reformat it into a file format that's more appropriate for analytics, in this case Parquet, and then import that into Impala and then query it from Impala. The specific technologies can differ a little bit, but the overall point is that you stitch together multiple technologies to try to cover the weaknesses of each. This certainly works. We have tons of customers that have been successful with this kind of paradigm, but it certainly implies some trade-offs. So first, it's inherently more complex. That mostly manifests itself when you actually run into problems. So if you've noticed that the process failed in one place or the other, it's sometimes difficult to figure out exactly what you need to do to recover from failure. It also implies that there is an inherent amount of latency between when data arrives and when you can report on it. Because you have to reformat the data first. You don't do that constantly because it implies some amount of overhead for actually doing that processing. And so you introduce some additional latency from when data arrives to when you can report on it. And in some cases, that's really important or the entire point of the use case. So it works, but there are certainly limitations. That same kind of paradigm on top of Kudu just looks like data goes in, data goes out. There's no convoluted multiple steps involved. Again, the primary point being to simplify existing architectures. So I've talked about various design facets of Kudu. First, as I said, if you're familiar with SQL or tables, Kudu should look very familiar to you. Tables have a SQL-like schema. It has a finite number of columns. In theory, the columns might be infinite in size, but like I would say that you shouldn't do that in practice. In practice, like probably looking at the tens of kilobytes per row. It could probably get bigger than that, but really it's not designed to be like a blob storage system. And typically you want a finite number of columns, probably in the dozens is kind of the high end. Those columns have types. Kudu has a relatively exhaustive list, but you'll typically not be interacting with Kudu directly. The types that you will be working with will be based on the higher level abstraction that you're using. If you're using Impala, you get the types that are in Impala, and we've done the mapping between the Kudu types and Impala types. Tables must have a primary key. That primary key has to be unique. I'll talk more about that on some further slides. Kudu supports fast, alter, and other metadata operations. So if you have an operation that seems like it should need to touch all the rows, like you're adding or dropping a column that doesn't have a default value, but in fact doesn't touch all the rows, it's just a metadata operation, it should complete like a few seconds. We have direct APIs. The two supported ones right now are Java and C++. There's also an experimental Python API. I expect more in the future. But again, we expect that most people will choose to interact with Kudu through a higher level abstraction rather than directly. But if you want to work with it directly, it has APIs that are pretty similar to other NoSQL databases, gets, puts, short scans, etc. It should be pretty familiar. We've built the first series of integrations. We're definitely not done. I would expect probably the most next important one that we haven't done is Hive. But in the fullness of time, I would expect us to do integrations kind of across the stack. Currently, we've done Impala, Spark. Spark is a data frame implementation, so that includes Spark SQL. Spark SQL support includes things like predicate pushdown, so it's not just a drop-dead, dumb implementation of it. There's like some optimization that's there. We also support MapReduce through a Hadoop input-output format. We support pulling data out of databases and pushing it into Kudu through Flume. And there's a community integration with Drill that we didn't build, that the Drill guys actually built. I would also say that if you're looking for a place to contribute to Kudu, this may be like the easiest place to get started. If you're working with a tool that we haven't integrated with, it's the kind of contribution that doesn't necessarily require you to get into the guts of the code. And as I said, we're very actively soliciting contributions. If you potentially want a commit bit on Kudu, there's definitely not an easier time to do it than right now when it's relatively new software and us just hitting our 1.0 release. But again, if you're thinking about places to contribute, this might be a good one. As we already know from trivia, tables are divided into tablets. Tablets are effectively partitions. If you're familiar with the HBase terminology, regions and region servers are almost directly related to tablets and tablet servers. Each tablet has a variable number of replicas. 3 is the default. If you're really paranoid about data loss, you can make this whatever number that you want, as long as it's an odd number. But 3 is the default. Things are kept in sync through a distributed consensus system called Raft, which is based off Paxos. But none of that's really important. Basically, just does distributed consensus versus synchronizing through a master and like a standby master kind of relationship. Tablet servers are just standard Linux commodity boxes, and tablet storage on a server is fully decoupled from the rest of the distribution. Kudu has all of the basic, or I think basically all of the partitioning schemes that exist, which roughly divided into like range-based schemes and hash-based schemes. Hash-based obviously has an advantage of spreading stuff relatively evenly or completely evenly across the cluster, preventing hotspotting, but it does mean that every server is involved in every query. Range-based partitioning means that data is contiguously located on individual servers. That makes it so that an individual query may only resolve to a specific server, which is good for concurrency, but it means that you might have hotspotting because some data, especially if you take a partitioning scheme like time-based, might be inherently more interesting than other data, and so some servers might be more utilized than other ones. So all that to say, like I think those are the basic partitioning strategies that exist. Kudu has both of them. They can also be used together to sort of cover a little bit of the weaknesses of each, but flexible partitioning schemes, basically whatever you want to do that I think is implemented in any other database you can do on top of it. Kudu is column-oriented storage. I'd say that there's nothing inherent in the architecture that means that we couldn't implement a row storage scheme, but the initial one that we implemented is column storage. And we did that because I think that it's true that the vast majority of open source use cases, and also the vast majority of use cases that Cloudera customers implement, are column-oriented analytical use cases. And it is true that for analytical use cases, where you only access part of the table and you're trying to do big aggregations, that column-oriented is far superior to row. That doesn't mean that there are not row-oriented use cases, and I'd say that those typically are more operational use cases. And it's quite possible that we add row orientation in the future, but currently the column oriented is the really optimal. As I said, every table has a primary key. That primary key has to be unique. The key can be either an individual value, an individual column, or it can be a composite key that comprises several different columns. We don't currently have a lot of facilities for like generating unique keys, so it's something you have to provide. I think typically that's relatively straightforward, but it's quite possible that we add like some primary key be generated in the future. There are also some constraints that the columns can't be Booleans, the columns can't be nullable. The columns also have to appear at the beginning of the table. That last constraint, I think, is just an artifact of us not having time to fix it. Like, there's absolutely no architectural reason that should be the case, but that just happens to be a current limitation that we'll get back to. Rows within a tablet are stored in primary key sorted order. This is probably most important to consider if you're thinking about encoding schemes. So if you're doing something like run-length encoding or dictionary-based encoding, those are more effective if data is contiguously ordered, and you can get some additional space savings. So you need to think a little bit about your primary key design. I think it's probably not as central to like system performance or as complicated as you might see in some systems like HBase, but it's also something you should conscientiously think about before you store your data or store a large amount of data. Kudu does have a master process. This master process is basically just a special tablet. It is purely metadata about the location of where other data is stored, and typically it's not in a hot path. So basically all it does is when you issue a query, you'll first go to the master server. The master server says, these tablets have the data that you're interested in. At that point, the information is cached on the client, and future requests don't have to go back through that master process. It also is maintained through the same way that normal tablets are maintained. And I'd say that we've seen this not become anywhere close to like an overall system performance bottleneck. It's extremely lightweight. It's basically just pointers to where information is stored. Kudu is obviously fault tolerant, and it both accommodates transient and permanent failure. So if you have a transient failure, so a tablet server has gone down, it will wait around for a configurable value. By default, that's 5 minutes. And basically what happens is, if it's a follower, so this is the tablets that are not responsible for declaring what the current state of the world is. And I should step back, there are basically two tablet holes. There's the leader and the follower. The leader is responsible for saying, this is the current state, and anytime there are modifications to that current state, is responsible for acknowledging that those changes have been propagated to the other follower states. So if there's a follower failure, the leader can still achieve majority. There's still enough replicas to actually return values. And it will wait around, and if the other tablet server comes back within that configurable window, things will just seamlessly pick up, just a momentary blip until it rejoins the cluster. If there's a leader failure, it's a little bit different, because at that point, until I acknowledge that there is a new leader, I can't actually make any modifications to the data. And so this happens much quicker. I believe this is also a configurable value, but effectively there's always heartbeats going between the leader and the followers. And if the followers notice that they haven't received a heartbeat from the leader in the last 5 seconds or so, they'll hold an election and create a new leader that is then responsible for what is the current state of the data. If the leader then is restarted within that 5-minute window, it will rejoin the cluster, but it will join as a follower instead of having those leader privileges. So it's just the process you would expect based on the consensus algorithm. A new leader is elected, things pick up seamlessly, you don't need to make any action. We can tolerate a certain amount of failure based on the number of replicas that you keep. That formula is just n minus 1 divided by 2. So if you want to be able to tolerate more failures, you can have more replicas. Again, the default is 3. For permanent failure, it's a little bit different. So if a leader notices that a follower has been dead for more than 5 minutes, effectively we're now in a state where we don't have enough copies of the data. So we've said that you need to keep at least 3 copies of the data. A tablet server has failed, so now I only have 2 copies of the data. I waited long enough for to give a chance for the tablet server to return. We've exceeded that period of time, so I need to start copying data. So the leader will pick a new tablet server to move the data to. We'll then begin replicating the data over to the new server until we're back to a fully replicated state. If a leader fails, it's a relatively similar process. Most of this is relatively seamless, but there are some cases where you actually need to make some config changes if you've lost an entire server to mark it as completely dead. Otherwise, it can potentially be pulled for state. And again, if you want to completely remove a node in the cluster from having any of these roles, there is a config change that needs to be made. I think that this limitation goes away in time, but that's just kind of the current state of the world. Kudu does keep consistency relatively similar to HBase and a lot of other modern systems through a scheme called MVCC, which is multi-versioning concurrency control. I may be missing that third one a little bit. Close enough. But basically the idea is that when you make a modification to data, either you delete a row or you update a row, instead of actually doing it in place, I instead mark that the old row is no longer current, and I insert a new row. And then when I query the data, I look for the most recent version, and that's what I return. And then periodically, I need to clean up that old crufty data that's no longer valid, and I'll do something called a compaction. So I'll take and remove those old versions of the row, and I will only be left with the current versions of the row. There are two client consistency modes in Kudu. There's client propagating consistency, which is the default mode, and there's commit wait consistency, which basically is some of the I think some of the more innovative stuff that the Kudu team has done in terms of synchronization of clocks without like atomic clocks. But basically, it turns out that one of the trickiest problems in distributed system is just knowing what time it is exactly on particular nodes, so that you can properly sequence events. And this is a way of certifying or interacting with a centralized time-based server, so that all of the individual nodes can agree on what time it is. And it allows you to do some more consistent guarantees than you otherwise would do in a distributed mode. I think that most of that is pretty immaterial, and you stick with the default and you get the default consistency that you would expect. Writes in Kudu actually go through a multi-stage process. So it is a column store, but it happens that when you're doing writes and updates, it is almost exclusively true that typically those operations operate on entire rows at a time. So when data is first ingested or when it is modified, it's more efficient to operate it on a row-based scheme, and that's what Kudu actually does. So it has an in-memory row set format that accepts the updates and changes to individual rows, and then it periodically flushes that data into the column format on disk. The data is immediately durable through a write-ahead log, so actually persisted on disk. But periodically that data is flushed back into the column format. Updates go into an in-memory store called the delta store, and this is effectively those multiple versions of rows. When I'm going and looking up what the current value is, I look at the deltas. Those tell me what changes have happened. I periodically compact those deltas together, so I'm only left with a single row. It's also, I think, one of the more innovative or nice things about Kudu is compaction happens incrementally all the time. So if you've worked with other NoSQL systems, you can run into situations where you have a major compaction where you need to rewrite an awful lot of data at once. Kudu has a background maintenance process that's constantly taking a certain amount of system resources and always incrementally compacting, with the goal of never doing a major compaction that rewrites an awful lot of the data, and therefore trying to give you like tighter bands in terms of the variance and latency you can expect. It's possible that won't always work, but I think in practice we've seen that this background maintenance process has been pretty good at keeping up with the incremental changes that have happened and keeping ahead of these compactions. On reads, there are two modes. There's read latest, which does what you would expect. It reads the latest version of the row. And there's also another option, which at this point I'd say is still experimental, which is read at snapshot. There are some database systems that have features that are similar to this. Teradata has a feature called temporal tables. These are basically querying the data as it existed at a particular point in the past. So you can say, select from this table as if it was like a week ago, and you'll get the answers as they existed at that point. We're able to do that because we have the old versions of the rows, the deltas that have happened. and it also implies that how far back in the past you can go is determined by how often you clean up or how much window you keep in terms of the amount of deltas that you keep around. I'd say that we haven't fully exposed this feature in the higher level tools. So I would fully expect to, say in Impala or Spark SQL, add table features that allow you to do this. But right now this is just a feature that is directly supported through the direct Kudu APIs that I would expect to be added to these other tools in the future. So I'll talk about 2 production use cases, and after that I'll hand it over to Cory to talk again considerably more detail about the use case that they're implementing and some of the thought process they went through to choose Kudu. These 2 are production use cases. They've actually been in production for a decent amount of time. I think this particular one's like 6 months or so, and the next one's relatively similar, maybe a little bit newer. This first production use case is at a company called Xiaomi. If you're not familiar with them, they're the largest handset provider in China. They're interesting because in 2012 they didn't exist. Today they have 700 million customers. And so you could expect that if you go from 0 to 700 million in a few years, you have big data problems, and they did in fact have some problems that they weren't able to solve with the existing tools that they had. The actual use case here is with each of their handsets, they ship a series of applications. Those applications send back information, and they want to know if something weird has happened. So effectively, they push out an update. They notice that all of a sudden, no one is using the application anymore. Like something has probably gone wrong. And so the value of the system is ultimately determined by how fast they can recognize that something's gone wrong and how quickly they can take corrective action on it. So the previous architecture that they had looks very similar to the slide I showed you a little bit ago about like a gap-filling architecture that tries to stitch together multiple systems. Also, if you're familiar with it, this is sort of a form of Lambda architecture where there is a fast feed of data and there is a batch feed of data. So they're ingesting data in a system for batch updates. They were also using HBase as that updatable partition because some data could be restated in the past or could just be erroneous. Or they had another issue where they had something called slowly changing dimensions, which is where you've got facets or things that describe your customer that change over time that need to be updated in place. They then took this data that was stored in HBase, massaged it through effectively like ETL processing in Hive that could map reduce, produced Parquet files. They then queried through Impala. So this is really similar to the architecture I showed you a little bit ago and has the same sort of trade-offs that you would expect. And the primary problems they had was the value of the system is determined by how fast they can get data from end to end. There's inherently an amount of latency that's introduced because they're reprocessing this data into Parquet files. And in their case, they had a minimum of an hour latency between when data arrived and when they could report on it. And in some cases, it was up to 24 hours later. And so the value of the system is greatly degraded because of that latency. So they basically replaced most of that architecture with Kudu. They still have a bit of a batch system that is meant for overflow. So if Kudu, for some reason, couldn't keep up with the updates or went down, they have another system where this data can be pulled, or can be collected and then pushed through Kudu at a later time. I actually don't think they've used that to this point, but it is the only complication to the architecture that I'm showing you. Besides that, it's effectively data goes into Kudu, data isn't queried through Impala off of Kudu. They're now able to see data that arrived about 10 seconds ago, where previously they had to wait about an hour. This is also a pretty substantial system in terms of size. This is about 100 nodes and is multiple petabytes at this point. Again, has been in production for about 6 months or so. This next one is JD.com. This is the second largest retailer in China. They're basically like an Amazon.com, but obviously in China versus the US. And their data problems look pretty similar to any other online retailer. And I think that I showed this one basically as a proof point that systems that previously would have been deployed on legacy and commercial software can be deployed on Kudu relatively seamlessly. So they do basically big reporting queries One of their primary use cases is something called sessionization, which is determining which clicks form a single coherent shopping session. This actually ends up being relatively complicated because sessions are now like really durable. I'd say typically minimally they last for 24 hours. They can last months. And so you can't just look at a session ID and say that that is a shopping session. You need to group a bunch of data together, perform some analysis on top of it to say that this was one individual shopping session, and all of your analytics are based on top of that. This is a very substantial system in terms of volume. This is about 200 nodes. They had a shopping day relatively recently where they pushed 10 billion transactions through in a day, and at peak they were pushing more than 10 million a second through the system. I think this is nowhere close to what the system could actually handle, and you could actually achieve considerably more than that by just spreading the data thinner and deploying more nodes. But the size of the system is pretty substantial. There are not a ton of use cases that are this big, especially that are implemented outside of commercial software systems that are inherently really expensive to actually implement at this scale. So it was relatively quick, and also I'd say relatively high level. If you'd like more information, there's deeper information. There actually is quite a bit on our website, which is getkudu.io. There's a technical white paper that goes down to a pretty low-level architectural detail. There are also ways for you to get help from the community. So there's forums that are on Cloudera, there are a dev and user mailing list. Probably the most popular way right now is we do have a public Slack channel that all of our developers, as well as many of our customers, hang out in. You should certainly be aware that that channel is public, so like don't ask for help with a query that contains like a social security number or something like that. But I think that we've been pretty good about getting answers back relatively quickly. There's certainly ways to get help if you need it. So as I said, next part of the session will be from Cory Isaacson. So he's the CTO of RMS, which is a risk management solutions services. They provide analytics on top of insurance. He's previously founded several companies. He's also written several books. But I've been really happy and glad that he's been supportive of Kudu and really interested in seeing the use case that he's got going into production.
So that was a lot for Michael to cover in a very short amount of time about a very technical product, right? So I'm going to try and give you more of a real-world picture of Kudu, how we use it, what we're planning on doing with it, and how we selected it in the first place. So anyway, I'm the CTO of RMS, as Michael said, and what our company does is we're the largest provider of catastrophe models, software models in the world. So that's what we do. So how many of you have worked with key value stores? Okay, a few of you. How many of you have worked with big data stores, HDFS, scanning Parquet files, things like that? Okay, a few also. All right, how about regular traditional RDMS? Okay, good. So that's the majority, right? So we've all been in that boat. I started out, and I'm going to date myself here, but I started out as I had the largest independent Sybase consulting company. That was one of the first companies that I had. So when Sybase was a really hot product and growing quite quickly until some things happened, it wasn't so good anymore. But that was the predecessor for any of you who've used Microsoft SQL Server. That's where that product came from. But I've worked with Oracle, I've worked with Postgres, MySQL. Anyway, the last company that I had before RMS was basically involved in scalable database technology. So we did a lot of research and we understood how this really worked. And we tried to do it with traditional databases, and I can tell you it was really a hard job to do. We actually were pretty successful at it, but it was very, very difficult to put that together. And so we had some of the first scalable MySQL implementations in the world. And actually, I heard recently that Pokemon Go is actually running on one of those systems. So that's pretty cool. So anyway, so the thing I want to talk to you about though is like, what is it? How did we look at this from a real world perspective? About the technology. Now, we were attracted to Kudu because when we first started reading about it, we actually saw that Kudu had more of the characteristics of a traditional database than any other big data system we had seen. So that was a very, very big plus because, as Michael said, it's a combination of a column store and a read-write store for key value type objects. but it does it in very, very clever ways, and I'll give you some examples of that as we go through. Anyway, so what is catastrophe risk? So what do? Is we basically simulate the effects of all the bad things in the world that can happen. So hurricanes, earthquakes, floods, any of the 7 plagues, we handle them. So that's what we do. And so we do this for insurance companies. And the reason we do this for insurance companies is who remembers like Hurricane Andrew? Right? So Hurricane Sandy, probably all of you know even more recently, right? But so when Hurricane Andrew happened, there were a lot of insurance companies that were undercapitalized, and so they went under. And so it became actually a regulatory requirement now. If you want to do, basically wind insurance or hurricane insurance in Florida or any place on the East Coast, you have to actually be certified and actually have proof that you have enough capital to withstand certain kinds of events. So the way the models work is they're event-based, and what that means is we actually take historical. We have 250 people in our model development organization. They basically take historic events and they basically predict what future events could be like. So think of our hurricane model as something that has something like, I think, 35,000 different hurricanes that can be simulated. We take that and we put that against an insurance portfolio, and we basically say what's the damage on each of those structures, and then we actually have a financial model as well, and we can basically take that damage. So let's say that house is going to be damaged 5%, this other one's going to be damaged 7%. We can actually figure out what the value of that is and actually put that through the actual insurance contract logic. So that's a really key strength of what we do as a company. So basically that's the way it works is we start with what we call exposure, which are assets that you want to insure. We basically simulate the events against them. We compute the damage, figure out how much it's going to cost, and then that adds up to potential losses, and then we have basically lots of different ways of looking at that information so that analysts can figure it out. So one of the reasons that something like Kudu was very important to us, I mean, who here has an application where you actually have to query a lot of data? Okay, cool. So how many of you have data that you want to query that actually changes? Like you want to update it? So that was a big deal for us, right? Is can we get something that was basically a read-write store that we really could query in a fast-changing basis. And that was very, very important to our application. Why? Because our historical product, what we've been doing for, I think, 26 years now, is basically a SQL Server Windows desktop application. So most of the customers run it on a single machine. Some of them have small clusters, maybe 8 machines, something like that. But basically, imagine that we're moving a bunch of analysts who work with these models from SQL Server, and we want to be able to record that same kind of experience with another type of database. So Kudu was the closest thing. When we looked at all of the other big data technologies, we were going to have to really compromise on what we wanted to deliver for customers. So I just want to show you a little bit about the data model that happens in insurance. This is a very conceptual picture for any of you. Anybody here in the insurance market? Oh, that's good. Oh, one. Okay. So I actually talked at this same meetup about, I don't know, a year or 18 months ago, and there were actually some people in the audience who really were familiar with our models and other people's models, and I got a lot of tough questions. So if you want to ask somebody later, we can. But anyway, so the idea of insurance is just a contract. When you have insurance on your home, what you're doing is you have a contract with the insurer that says, in the event these things will happen, we'll pay you this much money under these circumstances. So that's how an insurance contract works. But insurance companies do more with those contracts. What they do is let's say you have Allstate as your insurer that you buy insurance from. Well, Allstate, what they will do is they'll run our models and they'll figure out where might the tipping point be for their portfolio based on how much capital they have. And they'll actually sell a portion of your policy, along with a lot of other policies, to a reinsurer. And the reinsurer then will spread the risk out further. And eventually the risk gets spread out to the bond markets and other things like that. So it just constantly is spreading the risk out across the world. So you can imagine that all these people need to say, how much capital do we have? What are the potential risks for what we have? We don't want too much concentration here or here. And so they're all evaluating these pictures all the time. And that's really what we do. So from a contract, the next thing we have is a risk item. A risk item is a physical thing. It doesn't have to be physical, but usually is, that you actually want to buy insurance on. So if you buy health insurance, that thing is you, right? If it's insurance on your house, then of course it's the structure and things like that. Then we have what can be what's called a schedule. So sometimes contracts are very complicated. If you're, for instance, insuring Walmart and they have 1,000 Walmarts in the contract, you don't want to have to list all those in the contract itself. So you have something called a schedule, which is a big list of all the things that you're going to be insuring. But basically, a contract always refers to risk items in one way or another. That's really what you're talking about. So then what we do is we take the contract and we group them into portfolios. And that's just an arbitrary grouping that someone has. So it could be my East Coast portfolio, it could be my Northeast portfolio, it could be for a specific business unit, it could be a specific kind of business. So really portfolios are just arbitrary groupings, and that's what you're typically using to buy reinsurance. You say, I want to take my portfolio of this particular character, I think the loss risk is too high, and so I'm going to actually sell part of that to somebody else. And then what we do on top of the portfolios is we have people have to group them into an organizational structure, these portfolios. So again, it could be reporting structure, financial structure, all kinds of different things. This is very, very similar to how you would organize, by the way, a stock portfolio in an investment firm. It's really not that different from how people look at this. It's just instead of things that you could make money on, assets, it's really things you could lose money on. So that's what you're evaluating all the time. So now, the thing about this, though, is that there's a lot of attributes involved, especially in risk items. So for instance, we can have a risk item for real property would be name, address, construction type. You know, we want to know all these things, right? Because the models are based on what's going on. So if you have a concrete house in Florida, that's going to withstand much more wind force than if you have a wood frame house. So those kinds of things are very important. In an earthquake, you want to know what kind of soil it is. Flood, what's the elevation, there's all kinds of different characteristics like that. So basically, over the years, as our models have gotten more and more sophisticated, in this core SQL Server database, which are very hard on the database itself, we basically just added all these fields all the time, right? So there are hundreds, if not thousands, of attributes that go on with these things, and so it's a very complex problem, and you often need to be able to query on any of these things, so you can't really predict it. So that made a very, very big challenge. So the other thing is, this is a very, very big data problem. Matter of fact, I realized it was humongous data when I first came, and I'll show you why. Because basically what we do is we basically query exposure data. So that's pretty big. Exposures, a portfolio might have a few 100,000 to a few million risk items. That's a very typical size portfolio. And basically, we get that exposure data, and then what we do is we actually do and compute what we call the hazard. So what's the hazard? That's how fast is the wind for that particular event, or how deep is the water for a flood. That's really what's happening for that particular location. And then what we do is we basically get hazard data out of that, which basically explodes, because now, let's say we have, again, our 35,000 events, and we have millions of risk items in our portfolio. Now it's 35,000 times millions, and that's in our simplest model. That's the models that we've had for many, many years. We have more complex models that do it a different way, and they can actually have 1 or 2 orders of magnitude more than that as far as actual output. So then we take the hazard and we actually compute the damage. So then we say, okay, if the wind speed is coming from this direction and it's this kind of structure and it's going to hit this way, how badly is that particular structure going to get hit? That's really what we do then. Then what we have to do is take all of those damage results and then put it into our financial model, and we say, you have insurance on your house. What's the deductible? How much is the damage? What's the value of the house? What's your deductible? What's the limit on the policy? All those kinds of things come into play, and those policies can get very, very complicated. The logic can be quite significant. But so we have to do that for every single risk item for every single event. So it's a multiplicative problem. And then we get results out of that, and then we have to write it all to a results store at the end. So those losses are actually a very simple data structure. The exposures coming in are a very complicated data structure, but there's a ton of them at the end of this. And so I call this the data explosion of risk management. So that's really what happens is we're really, I have a joke which I shouldn't say too loudly, but I told our CEO, who I'm very good friends with, I said, you make more money off of made up numbers than anyone I know. But there is actually a lot of science to it, and it really is fascinating. So anyway, so why is it really a big data problem? Because exposure data basically is the input again to the models, We have large numbers of attributes. So again, we need the value, we need the location, things like soil type. I mean, there's all these different things. And we really have, scientists who study these events and study these types of hazards. And they actually need all of this information about a given event. They study the engineering of different kinds of buildings so that they can come up with as accurate as possible of a prediction. And we do have, by the way, the best models in the world. We've been at it the longest. And so they're very, very high fidelity models because they take all these different things into consideration. So the data can also be very large, the exposure data. So it is a big data problem all by itself, so just the input. And what I mean by that is a given portfolio can be millions of assets. That's very common. But a single insurer or reinsurer, if you get a big company, they can have billions of those when you put it all together. So now we have billions with lots and lots of attributes. I mean, tons of attributes. Like it really surprised me how much, right? And then on top of that, we have these financial contracts, right? The policies themselves. Well, these contracts can have all kinds of terms and all kinds of attributes, and you have to be able to query on all those things too. So it's not just this, and it's like a very, very complex query problem. So that side of it is reasonably big data, but it's very, very complicated data, and you have to be able to query on any column. So it's a key requirement for us. So then we have basically the simulated claims data. That's what comes out of the models. So we're basically simulating what would happen for insurance claims on that given portfolio. That's really what happens. And so basically it's a multiplicative problem like I told you. So we can get 100 billion losses out of one model run, and somebody might run that model 5 times on that given model. And if you go to our newer models, I've actually seen projections much bigger than that. Right? So you're talking about terabytes of data that can be generated very quickly, and we have to be able to write this data and be able to query on it to be able to do the analytics at the end of the day. And then the real problem is that at the end of all that, almost all of the metrics we want to know from that is the top end type queries. So that's almost always what happens. So now I have this 100 billion things, and I say, well, if I'm looking just at this particular zip code in Florida, what are the 10 worst events or the 10 worst occurrences? What are the things that are going to actually cost me the most? Where's my biggest probability of those particular losses? And so we're constantly with these metrics having to scan all of the data, sort it based on the query, and then evaluate those top end losses. It's a very, very challenging capability to be able to do. And I've been doing a database work my entire career, and when I saw this problem, I went, well, this is really a different order of beast. So it really is very difficult because these metrics are not additive, they're sorted. So that really makes it very, very challenging to do. Okay, so then we had the typical non-functional requirements that probably all of you do. So it had to be scalable, reliable, high performance, high concurrency, but we also wanted minimal development time and risk. So I'm a risk taker, I've been doing new technologies my entire career. I can tell you that we are not risk takers, we're risk managers at our company. And so for me to actually get the idea that Kudu could really help us and actually minimize our development time and risk was a rather lengthy process. I can tell you that it took a lot, and it was very good because we basically had to have all of the business executives in charge actually really understand what they were getting into and why it was worth the risk, and why it kind of came down to, I had a joke, but I said, do we trust our guys to do this stuff on top of these big data technologies, or do we trust the Kudu developers? That's really kind of the way I looked at it. And I said, this is their day job, and it's certainly not our day job to do this kind of thing. So anyway, so far it's been a very good bet. We're still relatively early on, but believe me, we had a lot of questions about how new Kudu was. We definitely were working with it way before it was 1.0. And it was kind of a very, very good experience. So anyway, so in summary, how do you take 1 billion plus exposures, be able to query any part of that on any one of these hundreds or thousands of attributes, and be able to run that through the models, and then take trillions of losses and be able to sort them, no problem. All right, so we did a very extensive technology evaluation because again, we really wanted to know if there was an easier way to do this. And we worked with almost every database you could mention, right? So we looked at Cassandra, and we looked at, we actually built it before with MongoDB, and that failed. We used Elasticsearch. We did Apache Ignite. We looked at MonetDB. I don't know if any of you have seen that, but that's an open source, column database from Europe. anyways, we tried all of these different things, MemSQL, Spark and Parquet. I mean, we really covered all of this. This was about a 15-month effort to actually investigate what we had to do and how we were going to put this together, because it really was not a very simple problem. So we basically looked at the features, we did performance and scalability tests, we did reliability and failover tests, all the kinds of things you would expect. But really, what engines were really going to have the characteristics that we actually needed to solve this problem. So I put together some slides for use internally, but I thought I'd show them to you. So this is really how we explain how data engines work and what our choices actually work. And so this might be an eye test for some of you, but I'll walk through it. So anyway, but basically, you have your client that's going to be doing the queries. And what we knew we needed was we needed a query engine, we needed a storage engine architecture, and a storage tier. Those were the three basic tiers in any database system that we had to work with. So we said, okay, what are our options to be able to do this? Well, the first decision that we actually made, because we had already been using it very successfully, was we said we're going to use Apache Spark and data frames as our query engine. So I made a very important point about this, is that Spark is actually the thing that's doing most of the complicated work in our system. So when you look at a database, either writing or reading, Spark is doing the most of the complicated work. So anyway, so then we had to look at storage engines and storage tiers, and we evaluated a few basic options, many of the ones that Michael already talked about. But I'll give you an idea of what that looked like. Okay, so now basically we had that storage engine, and then we said, okay, our storage engine could still be Spark, and we could just use Parquet files. So could we actually do that? Well, Parquet files are great for scanning workloads. It's a great system for column-based workloads, but you can't do updates. And these things change a lot. So for instance, we get more information about the real estate assets or the other kinds of assets that we're actually tracking. That happens all the time. So we have to be able to update those kinds of things. The contracts change year to year, so all of these things get updated. The terms change, all that kind of thing happens very, very quickly. So typically, the exposure data that I told you about, the actual things that we're actually insuring, that gets updated frequently, and it has relatively small updates. So we have to be able to update small things, but we have to be able to query all of that in the context of the really big results data. And the results data doesn't really change too much. So those are the characteristics that we had. So we looked at this and we said, how would we even do this with Parquet? I mean, we'd have to make copies of Parquet files, make changes, copy them back over. It looked like a very daunting task to be able to do this in a reliable way. So then we said, okay, what if we use Kudu? Because we found Kudu, and this is the architecture that we actually ended up with. And we basically said, let's have Spark as the query engine on top with data frames. And in a data frame, we actually were able to use Kudu as the storage engine and Kudu tablets as the storage tier, and then Parquet for some things. So we basically took some of the non-changing things and put that into Parquet, and we basically took the things that change a lot, like contracts and things like that are smaller data, and we actually put that into Kudu, and it worked out quite well for us. And the nice thing about Spark is we could join these things, and we could make it look like one consistent set of data. So, and we also, by the way, put all of the loss data, the big loss data, also goes into Kudu. So that's also been very, very effective, because it's very easy for us to sort it and do different things that we have to do to be able to find what we're looking for and solve that top-end problem in a very, very good way. So, so anyway, so this is the architecture that we picked, and we started testing it. Now, when we started, there was no Spark data source for Kudu, so we contributed one. And the Cloudera team helped us with that, and it's actually terrific. We use it all the time now, and it's actually been just a great component. So, as Michael said, that's a good way to contribute, is to just make it work with more different kinds of query engines. It was, I don't think we spent 2 weeks on it even. It was actually pretty good for getting this done. And then we added more enhancements over a few months, but really we didn't have to invest a huge amount of time to get that done, and it was a key capability because at the time it just wasn't in the project. So if we basically look at the different kinds of queries we do and what the effects are of these different databases, one kind of query is find all the risk items that are in a single contract And let's say there are 10 risk items in that contract. That's what we want to get back. If we have to query that from Parquet files on HDFS, right, which is very fast, right? But remember, if we have 1 billion of these and we want 10, we have to scan the entire Parquet file. So we have to scan all billion to find those 10. There's no other way to do it. With Kudu, because we made it from the primary key, we can actually go in and we can actually say we have several 100,000 risk items partitioned, as Michael talked about. Partitioning is great. I'll talk about that in a minute. But we basically have that. We can now go directly to those 10 risk items and get them like that. So that's awesome. That's a very easy key value store use case to understand, but it was very, very effective and much, much better than using Parquet for that particular use case. So then we wanted to compare also what other choices were there, because we were asked that question, what else could we do? And so HBase was the alternative to Kudu. So that was the thing that we looked at. So the interesting thing about this was now we have to find all the risk items in a particular portfolio where zip code is 1, 2, 3, 4, 5, and the insured value is $1 million, over $1 million. So it's a very specific query now. Now we're getting out of the primary key and we're going into all of the columns. Well, because Kudu is columnar, we could basically scan the entire file in Parquet. That would work. But we could also scan it in Kudu, and we could actually have that fast-changing data that changes a lot of times, and we still could go ahead and do that kind of query. If we use something like HBase, and there were 100,000 of those partitioned in some way or another, we basically would have to do 100,000 lookups to find that same subset of things. So we might be bringing back 100,000 risk items, but we have to look at a lot of things and do a lot of individual lookups. So that was much, much worse than being able to do a column scan. So it really is, I hope I'm making the point, and Michael did too, is that it's really this combination of key value and column scans that allow you to do that really, really effective things with Kudu. So it was a great balance and a great mix for us. And by the way, we're using Parquet and we're using Kudu. My hope is eventually we just use Kudu. Life would be a lot simpler if we just had one engine, but we're able to make it work pretty effectively the way it is. So this is the architecture that we ended up with. We don't have to go into this in a lot of detail, but basically we have 2 data sources, one for Parquet, one for Kudu. We basically have the 2 different stores, and we basically can query any of those things and get what we want. But it comes back looking like it's a single database, which is really awesome. So now we can meet all of our use case requirements, including updates. And updates is a really big deal for us because, like I said, these things change, especially the exposure data, the contracts, they change all the time. There are customers that do not millions of updates a day, but certainly thousands or tens of thousands of updates a day. So we have to be able to have these things reflect reality. And I don't know how many of you guys, it was suggested, well, why can't we do eventual consistency, for instance, for updates? And I don't know how many of you have users that really like that, where they make a change and then they query the data and don't see the change. That's not so good usually. Right? That's a very difficult thing to explain to a user, especially when you're used to SQL Server. Very, very difficult. Okay, so in summary, I put together some strengths and areas that Kudu still needs to improve and add other features. So basically the strengths are it's very scalable, it's very reliable. There was a known issue with the reliability when we first started testing Kudu, and we couldn't replicate that issue. That's all fixed now, but we actually tried and we actually could not break it. So we did a little bit of our own chaos monkey, and it was actually awesome. We also scaled only up to 32 nodes, but with 32 nodes, we were able to manage a significant amount of data. So that was when I told you about a billion exposures. We were able to do that on 32 nodes, get very, very fast performance because we were able to partition based on portfolio and other kinds of things, so we could break the data up in specific ways, and that worked out very, very well for us. It has very fast updates, so we've been able to, we've seen the same millions of writes that Michael was talking about, so that's real. You can do live queries while you're making updates, and your queries are consistent. In other words, you're not going to get bad data, except for you have to remember that Kudu only guarantees consistency for one row. It doesn't do it for a set of rows. So we're having to do some things about that, but otherwise it's fine. Again, column scans, we talked a lot about that. But a key thing is, since, like I said, my last company was involved in scalable databases, I probably know every database sharding scheme that exists. Maybe not everyone, but I certainly have done a lot of homework and a lot of study on this. And we have a whole company, that's what we did. Kudu actually has the best way we know to do this. And it's two-tier partitioning. The engineers are very smart in how they decided to do this. And what that means is you have the option of basically, instead of just hash partitioning, if any of you have done that, modulus, write one row here, one here, one here, one here. What you can do is you can basically say, I want a particular range of data. So I can take a range of my primary keys from 1 to 1,000 here, from 1,001 to 2,000 here. So I can have a range, and within that range, you can actually hash among the tablets within that. So it's very, very effective for us because we were able to limit our data by range, and that's how we got ability to scale incredibly well. So most of the queries are amazingly fast from Kudu itself. There's a lot more overhead actually getting it into Spark and the data frame and all the way back over the network to the user than there is in the data engine itself. So that's really, really good, and they just added dynamic partitioning, which was a kind of a dream of ours. We didn't know if that was going to be now or a year from now, but it really is pretty amazing. So now you can basically redo your ranges, and you can add more servers on the fly, and lo and behold, it works. So it's really awesome. So the other thing was it really reduced our development time. If we didn't have Kudu, we would have had to build all of this ourselves. We had an earlier effort where we tried to build all of that, and I can tell you it was a pretty miserable experience. It was very, very difficult. And because I come from this industry, I know exactly how hard it is to do to get consistent writes between different stores. And we had a team that tried that, and it's just not a lot of fun. So it was really, really good. And then the last thing I want to say is the support has been awesome. I think that in the entire 9 months we've been working with Kudu, I think we've seen only 2 significant bugs in the entire time. Both of them were fixed in 1 day. So that was, I always throughout my career, I've managed hundreds and hundreds of software developers in my career, and I can always tell when somebody's good and has built a good piece of software because they can debug it quickly. That's something I always look for, and so that's certainly the case here. And of course, because it's open source, we looked at the code, and that was really nice too. Okay, so what's lacking? There's no transaction support. So this is tricky because it is atomic for a single row. Well, what if you have to write 3 rows and you want an atomic picture of that? That doesn't exist yet, right? So we're having to do a few workarounds to get around that. There's no security yet. So if that's important to you, for us, we were able to work around that because we could just do it at the Spark tier. So we use the query engine to do it. There's no native SQL support, so you have to have a SQL engine. I know that there's lots of choices. There's Apache Drill, and there's Spark, and there's Impala, and you have lots of choices to do that. But eventually, I would like to see SQL directly in Kudu. That's my wish list. But then you have to have a query engine, and then more tooling is certainly going to come over time. There's just simple things like a backup manager, all those kinds of things. There's some tooling now, but you can see room for a lot of other things. So all the things you're used to with any traditional database you work with, eventually over time Kudu will have those things. So it'll work really, really well. Okay, so now we can take questions from any of you. So if you want to come back up, Michael, and we can take questions. You can also email me, or you can find me on the Get Kudu channel as well. So if you have anything you want to ask afterwards, we can do that too. Sure.
I'm not clear on your definition of portfolio. Would that be like all the property that MetLife insures, something like sort of that large?
Yeah, the question is, what's a portfolio? A portfolio is any grouping of contracts that someone wants to make it. So it could be all of MetLife's business. That could be their whole book. That's a big portfolio. Or it could just be what do they have in New York.
So is there a whole spatial component also, where you're doing things like disaster, you need to know flood damage, foundation?
Absolutely. Absolutely. All of the, we have lots of mapping in our applications. I didn't show you any applications today, but there's lots of mapping in the applications, but also the models are very mapped and location-centric. So that the models know, one of the things that's making these newer models really a challenge is because the geo data for the world is getting much more granular. You can get data now that's down to incredibly small sizes, where before, we had only kind of big, square mile or something like that. Now it's measured in meters.
Next question.
Sorry.
months, you have published the findings of comparing different databases and how you can
Yeah. The question is, have we published the findings for comparing all the different databases? The answer is no, because it's a big competitive advantage for us. So there's a lot I'm not telling you.
Now, a follow-up question on that. You mentioned that it took you guys 18 months to evaluate technology, and I'm like, I think a lot of us actually do that almost every time,
Yeah.
different databases. What do you wish you had to make that time frame like shorter?
Yeah, so what could have made our evaluation time shorter? Certainly, if Kudu was further along and we didn't have to make such a persuasive case for it. And I think it is now. I mean, it's 1.0 now. But you have to understand when we started, like I said, we had developed this earlier with MongoDB and Elasticsearch, and we tried a lot of other things. That was a very arduous effort that didn't really succeed the way that we wanted it to. So to try something that would look like it was brand new was, like I said, it's we're growing up as a software company, and nobody had the same tolerance for risk that I have, sort of lived with all my career. I go, this stuff never works. You have to help make it better. But anyway, so I think it's a lot more proven now, and so now just knowing the characteristics, I think on paper almost you could say these are the kinds of things I want, and then do a lot fewer tests.
Isn't it dynamic partitioning with Parquet, where you can access the whole data set just by creating another partition in case of, let's say, not a directly in high format, like for your new things, and then querying it with anything, Hive or Drill for that matter will be comparable?
Yes, so the question is, could you use Hive and Parquet? You just have to
Or even Drill and Parquet.
And Drill and Parquet. The answer is yes, but with Parquet, you're never going to get the efficiencies unless you're writing big amounts of data all the time. So if you change just 3 things out of 1 million, it's not good for that use case. Then you have to use HBase, or you have to use some other technology. But then it's even harder to put those things together. So we were able to do it in a very, very seamless way this way, because we actually have a fast update.
And of course, if you don't have updates, right? So if you have updates that you're arbitrarily following the past, the only way you can update Parquet data is to effectively rewrite it. And if you have updates that are spread across all time, that can mean you have to rewrite everything. And
yeah, but if you create another, dynamic partition every time when you need to do updates and put your new data over there, but then when you query, it just reads the whole structure. It's kind of the same.
It's the case where, say that I've got 100 partitions, and I happen to have got an update in every single one of those in the last cycle that came through, the last batch cycle that I processed. Because it touches every single one of those partitions, I don't have one that I can change. I effectively rewrite the entire data set for all of time if I don't have updates.
Yeah, and for our application, it's exactly that use case. We can't predict what the user's going to do.
So you basically want us to combine the transactional and analytical in the same thing, the way that relational databases are doing.
That's right. And look, eventually, Kudu is going to be very much like a relational database.
Yes.
How big is your footprint, and have you tried in your comparison all of the database?
Comparison with what? Oracle?
When you compare it, let's say, have you seen Putin Oracle instead of Kudu?
I see. So did we try Oracle? The answer is no, because everybody had a lot of experience with Oracle, so we knew kind of what its limitations were. I had clients in my past life that used Oracle RAC, and it's not a lot of fun, very, very expensive. So open source was also a big help to us, so we wanted to be able to do that too. So, but we only needed, for the exposure data, at 32 nodes, we could handle what we thought was more than any customer would actually need to do.
What's the database size here?
In the terabytes, I don't remember how many. But yeah, but it's in the terabytes. But that's for the exposure data. The loss data can get much, much bigger. And so that way it can be in the petabytes eventually. But there, the query patterns are much more defined as well. It's only write once and read many times.
Last question.
Oh, sorry. The JD.com use case, like I said, is a very traditional analytic data warehouse and reporting use case that's over 3 petabytes now. It could be quite a bit of data. So 200 nodes and 3 petabytes covers an awful lot of the overall space.
Last question, Evening.
What is the size of the minimum cluster to work with this?
Well, if you're willing to tolerate permanent failure, it could be 1 node. But obviously, if you want the data to be durable, you need
That's all the time we have for Q&A. However, both of our speakers are here for one-on-one questions right now. Thank you so much, Cory, Isaacson, and Michael Crutcher. I'd like to ask everybody, there's extra pizza. If you find someone homeless or hungry on the street, grab a pie and give it to them. I'm serious, or you can take it home yourselves.